What does it take to get a number? The numbers that we read in books, see on maps, and hear in the news about the Arctic. Numbers describing sea ice thickness, snow depth, ocean and air temperatures, and clouds. Numbers that explain why the sea ice is decreasing and how that impacts all of us living on this planet. It's September 20th, 2019 in Tromsø, Norway, the gateway to the Arctic, and a team of scientists and crew are packing up and getting ready to set sail to conduct a year-long scientific expedition in the Central Arctic Ocean. It's called MOSAiC, the Multidisciplinary Drifting Observatory for the study of Arctic climate. MOSAiC is a scientific odyssey, a global community of researchers endeavoring to piece together the most comprehensive picture of the Arctic climate. I'm traveling with the scientists for 3 months, filming the expedition while they focus on gathering those numbers that might help us all understand why the Arctic is changing so quickly. Teams of scientists from over 19 countries, each tackling a different piece of the Arctic climate puzzle, will live together on board the German icebreaker ship Polarstern as it drifts with the sea ice across the Arctic Ocean for an entire year. There are many challenges unique to the beginning of an expedition. So much is involved just with the logistics of getting all the equipment on site, not to mention the very important containers of food to feed over 100 people for months, and fuel needed to keep the ship running. Once the ship is fully packed, a send-off party waves us goodbye, and we set out to study the Arctic atmosphere, ocean, sea ice, and ecosystem. After a week sailing across open water, the edge of the sea ice finally approaches, and the scientists face their first challenge: finding the ice floe. What is an ice floe, and why is finding the right one so important? The Arctic Ocean is covered in sea ice, and a floe is a piece of ice floating on top of the ocean. Ice floes change in shape and size depending on the season. They have their own life cycle of growth and melt within the larger Arctic climate system. Understanding the life cycle of this sea ice, from the time it starts growing in the fall to the time it starts melting in the summer, is key to understanding why Arctic sea ice is melting faster than it's growing. And to study the life cycle of this sea ice, the MOSAiC team needs to find a floe they can anchor the ship to, set up their instruments, and drift with for a full year, for its entire life cycle. Matthew Shoup, an atmospheric scientist from the University of Colorado Boulder, has worked with the German Alfred Wegener Institute for more than a decade to make this scientific mission happen.
We have a daunting task ahead of us: finding the ice floe. There's been lots of discussion so far, with differing opinions, and in the end it really just comes down to a balance. If we go with the thinnest ice, well, that ice might have a higher chance of breaking up early, and we would lose a lot of the program. If we go with thicker ice, well, we somewhat impact our ability to study that thin ice, but in the end, this will give us a better chance of drifting for the full year.
Why is it important to study all aspects of the Arctic simultaneously for a full year? Why are scientists studying the sea ice, the ocean, the atmosphere, and the organisms that live there? The Arctic climate system is a complex web of interrelated processes. To understand this system, you have to pay attention to these incredibly tiny details, even invisible details. You have to put numbers on those details, and because every detail is connected to others, you need numbers to describe those connections, too. One of these connections is called Arctic amplification. Arctic amplification is a feedback loop that describes how temperatures in the Arctic are warming faster than any other place on the planet. The sea ice covering the Arctic Ocean is very bright, so it reflects sunlight back to the atmosphere. However, the ocean is a much darker color and absorbs the sunlight. As the sea ice melts, the open ocean absorbs more solar energy, which only increases overall temperatures, further decreasing the sea ice cover. Thick sea ice was more widespread in 2008 when the idea for the expedition was born. In 2019, when we left harbor, it proved difficult to find. With help from the Russian icebreaker Akademik Fedorov, scientists aboard the Polarstern search for an ice floe where they can build all their research stations and install their instruments, a central observatory on top of the ice. For days, we explore different ice floes, hoping to find one strong enough to support a floating observatory, where measurements will be made from the ship as well as the research camp on the ice. On decision day, key personnel and scientists join together to pore over the results of their surveys, diagrams, measurements, and interpretations, and all describe similar experiences. Very thin ice, generally small ice floes. After discussing their options, the team agrees that the ice floe, now named the Fortress, is the best option to support a year-long project. This is the new Arctic, thin and fragile. It quickly becomes apparent to me that scientific knowledge isn't just about the brain, analyzing data, finding patterns, synthesizing ideas. Science is also in the body, in building tools, fixing broken instruments, walking out into minus 30-degree temperatures. You set up equipment on the ship deck. You get out onto the ice with chainsaws and cut holes through to the ocean below in freezing temperatures where exposed skin can burn and blister upon contact with metal, and protective gear is needed to avoid frostbite. It takes a team of scientists, technicians, and engineers working together for many days to set up the central observatory on the ice around the ship. Let's take a tour through the installation of the Central Observatory and hear from some of the scientists about their thoughts on fieldwork. This is ecologist Allison Fong when I ask her about the setup phase of the mission.
Science involves all of this manual labor. It involves building up your lab space and then breaking it down when you're working on an expedition or a station. You know, it's a blank slate is what you walk into. And so for your ability to do science, you have to build it. Science is about building knowledge. So building space to build knowledge is science.
The setup phase is also a critical part of research, explains atmospheric scientist Jessie Cremian.
I would say even the setup, even though it's mostly dealing with logistics, it is science because you discover different challenges that you encounter in setting up for such a study, and there are different conditions you might be exposed to that might help guide how you set up or how you do the measurements afterwards. So, for example, there's a crack that opened up in Met City, and I put a sampler there, and I kind of figured out how I would do that in that sort of circumstance here on out. So it's not just setup, but it's also kind of learning about what the conditions are you're working with and how to take the measurements in the future.
sea ice scientist Marcel Nicolas explains how important not just the installation of the instruments is, but all the prep work involved beforehand.
I mean, you have to build your camp, you have to organize yourself, you have to clean and dry and rinse your equipment every day. So when you want to get out there, especially in this cold, you want to have the perfect equipment, and so that needs a lot of time in the lab or in the workshop now to repair it, because everything you can do in here probably takes outside 3 times as long.
It's October already and getting darker by the day. Everyone is racing the disappearing sun and the onset of polar night, when the Arctic will be in constant darkness until late February. I was amazed at how much time and sheer physicality it took to set up all the instruments on the ice. The scientists were not only used to it though, they were excited to do the work because of the data they'd soon get to see. And that's the part that many of the scientists love, says doctoral student Michael Angelopoulos.
I mean, that's part of what drew me to field work. And then when I went to the field the first time, I got to experience just how challenging it is to collect data and how much fun it is to get your own data. And after I experienced that, I knew that I wanted to do research. It's part of the adventure.
Analytical chemist Katarina Abrahamsson has another way of explaining the adventure of fieldwork.
I think that in general, I am in love with measuring stuff, having to solve the problem of how will I measure this, and then you develop your method. It's fun. It's a lot of fun to be able to measure stuff, to interpret, and to get new questions.
It's midnight and the bridge of the ship is packed. After weeks of setting up the ice camp, the first major storm on the MOSAiC expedition, with 40-mile-per-hour winds, cuts through the central observatory. Everyone watches from the bridge as the storm breaks apart the ice floe, carrying the research stations across the bow of the ship. While the storm means a tremendous amount of work resetting up the central observatory, it also provides an invaluable opportunity for the scientists to study atmospheric events, sea ice dynamics, and oceanic forces. MOSAiC is all about connections between the atmosphere, sea ice, and ocean. Let's follow one of these connections from the atmosphere, down through the sea ice, into the ocean, and see how we end up back in the atmosphere. The atmosphere is full of tiny particles. Some of these particles, called aerosols, provide little surfaces for water droplets to form on, or ice crystals to freeze on, which leads to the formation of clouds. Atmospheric chemist Lauriane Kilivert is trying to understand how these aerosols form in the Arctic.
I am interested in what is going on with the chemicals that form aerosols, and then looking at whether or not those aerosols and which ones are important enough to impact the climate.
Atmospheric scientist Matthew Shoup is looking to understand those clouds better.
My favorite kind of cloud is Arctic mixed phase stratocumulus, and we've been having that for almost the whole of MOSAiC so far. Mixed phase clouds have both supercooled liquid water droplets and ice crystals. My research question? Well, I would like to know, why does liquid water exist at temperatures that are below the freezing point in all these clouds?
With help from a meteorological tower, Matthew and his colleagues are learning that the amount of liquid water and ice in clouds matters if you want to understand climate, and those aerosols drifting in the air matter too. So the team is working to put numbers on how all these things swirl together to make different kinds of clouds, which impacts the amount of sunlight that passes through to the sea ice. The sea ice, layered between the atmosphere and ocean, modulates exchanges of gases, heat, and light between water and sky. In order to understand the ways Arctic sea ice impacts these vertical interactions, scientists on the ice team, like Marcel Nicolaus, study the sea ice from below with underwater instruments.
The sea ice is a key element in the Arctic Ocean. It's also the element that makes the Arctic or polar oceans distinct from all the other oceans of the world. I'm researching how the sea ice freezes, how the snow cover on top of the ice impacts the amount of sunlight that passes through, and how much sunlight is there for the animal and plant life living in and under the ice.
To piece together the Arctic climate puzzle, MOSAiC scientists also study sea ice dynamics. Atmospheric and oceanic forces on sea ice can create pressure ridges, and pressure ridges form when the ice is pushed together to form little mountain ranges. These pressure ridges refreeze above and below the water, creating piles of ice that jut out above and below the sea ice cover. The sea ice and ocean provide a home for many Arctic plants like algae and animals like fish and microbes. Scientists on the ecology team, like Alison Fong, study the relationship between sea ice and animal and plant life.
One aspect that we're always interested in, which is why MOSAiC is a special opportunity for us, is that we're trying to understand how microorganisms become incorporated into ice as it grows. We, in ecosystems, aren't necessarily studying the physical properties of ice, so ice itself, but looking at ice as a habitat.
Atmospheric scientist Jesse Cremian studies microbes, which are tiny organisms like bacteria or plankton that normally live in the ocean and sea ice.
They don't usually get up into the atmosphere, but I'm researching how that's changing as the sea ice melts and as more of the ocean becomes directly exposed to the air. Now, certain types of microbes have a really special characteristic. They can help clouds form. And so when winds carry them high up into the atmosphere, they can become these tiny little surfaces for ice to grow on and can actually help ice crystals form in Arctic clouds.
Little surfaces for ice to grow on. She's talking about aerosols. Remember those aerosols that help clouds form? That's where we started, and we're back there again. Clouds affect temperature. Temperature affects sea ice. Sea ice and water affect ecosystems, which again affects the atmosphere. A complex loop of cause and effect. There are so many of these loops, so many complex interactions that cut across the Arctic system. And MOSAiC is trying to study all of them together and at the same time. Away from the bright lights of the ship, atmospheric scientists use a flux chamber to measure the exchange of invisible gases, like the greenhouse gases methane and carbon dioxide, between the ocean and atmosphere through the sea ice. Meanwhile, the ice and ecosystem scientists work together to take samples of sea ice called ice cores, cylinders of ice taken from the floe. Ice cores have layers of old ice and new ice, and these layers also contain chemicals and particles like microbes and aerosols. Ice cores are records of the Arctic climate system. Back on the ship, the ice cores are divided up and distributed between the research teams. Sleds carrying equipment are unpacked. Instruments are cleaned, rinsed, dried, and put away. After long days of fieldwork, the scientists return to their labs to process samples, organize equipment, and prepare for the next day. In the labs, there's still more work that needs to happen before the samples collected become numbers that can be analyzed. Ice cores are weighed, melted, and tested to determine their nutrient levels and biogeochemical compositions, and searched for life forms like algae and microbes. Some of the ice cores are sliced into very thin sections and placed between polarizing filters. Then, when light shines through the ice, different colors reveal the microstructures of the sea ice crystals. This is how light and color can be used to study the physical properties of sea ice. Somehow 3 months have gone by and it's late December. Time for the first group of scientists and crew to head home and pass work off to their colleagues. Since September, the Polarstern traveled 2,776.83 miles and drifted past the 86th parallel. The ship has been the scientists' entire world for 3 months, keeping them alive in the middle of the Arctic Ocean while they gather the numbers that will help determine why the Arctic is changing so quickly. The first part of MOSAiC may be over, but back on Polarstern, colleagues are already settling into their routine, finishing out the dark Arctic winter months. And there's still 10 months left of the expedition to go. 10 months left to collect data and Arctic numbers. What will happen next?